Hey, so this is Joe, and this is the fourth video of Chapter 13 in Stewart's Calculus, and we're going to be talking about velocity and acceleration with vector-valued functions. So the concepts here are pretty basic. They're not going to be too different than concepts for basic mechanics like this used in single-variable calculus. So basically what we have is we have a vector-valued function, r, that denotes a particle's displacement or an object's displacement. We can find the velocity and the acceleration of that object using these two identities. The velocity vector valued function is going to be the derivative of the displacement vector with respect to time, of course, because that's always our common parameter with vector valued functions, or whatever parameter you're using, but fact is there's going to be one, and this is going to be the derivative with respect to that one parameter. And then the acceleration of that particle is going to be, we're going to get an acceleration vector, which is equal to the derivative of the velocity vector with respect to the parameter. So these concepts aren't too complicated. And now we're going to get just a little bit more involved, and we're going to start talking about the parameter, or I'm going to tell you, we're not going to go too deep into this because this is more relevant for physics applications, which you will go more in depth in physics class and the like, but it's good to know about these right now for this course. We're going to talk about the components of this acceleration vector and what exactly those components are. So the two salient components of acceleration are the tangential and the normal components. And the tangential, that's denoted by the little t in the subscript, and the normal by the little n in the subscript right here. And so the difference between these is the tangential acceleration is the acceleration component that is perpendicular to a particle's movement, wherever it may be. And so this is important for when we're talking about an object traveling in circular motion. If this circle is the object's path, the tangential acceleration, the tangential acceleration is going to be tangent to its motion like this. So this is would be the direction of the tangential acceleration vector, and this is important for finding the torque on an object. And now our normal component is going to be perpendicular to its tangential component, and if it's a circle like this, the normal acceleration will be pointing inwards, and that's important for finding centripetal force. And so we have equations for these two components down here that you can find the formula for them in your book, but it's important just to memorize these. So the tangential acceleration is going to be the absolute value of the derivative of the velocity vector, or the magnitude, we can say. And the normal acceleration is going to be the curvature, if you remember from our last video how to calculate curvature, times the absolute value of the velocity vector squared. And those are the two components. We're not going to really deal with them too much in this video, and most likely you're not going to deal with them too much in your math class, or this course in any case. But if you're going on to take more advanced physics classes, this will be important. So now that we have kind of all the basics for velocity and acceleration using vector-valued functions, we're going to do one practice problem and then call it a day because it's not terribly complicated. So we're going to do number 10 on page 894 in your book, and we are given this displacement vector right here, this displacement vector valued function, and we're asked to find the velocity, the acceleration, and the speed of the object. And the speed, of course, is just the magnitude of velocity in the same way that speed is the non-directional version of velocity in single variable calculus. So first let's find the velocity vector, and so we've got our little theorem right here that the velocity vector is going to be the derivative of the displacement vector. So we take the derivative of each of the components here. The derivative of 2 cosine t is going to be negative 2 sine t. The derivative of 3t with respect to t is going to be 3, and the derivative of 2 sine t is going to be 2 cosine t. So that is our velocity expression. And now that we have velocity, we can find the speed, which is going to be equal to the magnitude of the velocity vector, like that. And we can find that by taking the square root of the sum of the squares of each of the components. So that's going to be 4 sine squared t plus 9 plus 4 cosine squared t. And so the 4 sine squared t plus the 4 cosine squared t is going to be equal to 4. So we're going to get a little 4 plus 9 under the radical, and then that is going to be a root 13. So we've got actually constant speed. That's kind of interesting. And now we need to find the acceleration vector, and our acceleration vector is going to be the derivative of our velocity vector, like that. So we take the derivative of each of the components here, and we're going to get a negative 2 cosine t. That 3 is going to become a 0, and the 2 cosine t is going to become a negative 2 sine t. And that is all she wrote. That's all the answers that we're going to need for that problem. So I hope that was helpful. This video wraps up chapter 3. Stay tuned for the next chapter. It's kind of the most important one of this whole the whole portion of differential multivariable calculus. We're going to start talking about functions in more than one variable, so not just vector valued functions, but functions, and partial derivatives. And that's where things start to get quite interesting. So stay tuned. Thanks.